Hello and welcome to another video. In this problem, we're going to be doing build array where you can find the maximum exactly k comparisons. Kind of a long one. And so here you're given three integers, n, m, and k, and you want to consider the following algorithm to find the maximum. So let's kind of walk through what this algorithm is essentially doing. So it's setting a maximum value at -1 and a maximum index at -1. It has a search cost. It's looping through the array, and every time you find a value that is bigger, strictly bigger than the maximum value, you make the maximum value equal to that, you make the maximum index equal to that index, and then you increment search cost. So it's essentially saying, like, every new biggest number you find, let's set our biggest number to that, and then every new biggest number we find, let's increment our search cost. And so we want to build an array that has the following properties. Array has exactly n integers, and every single number in the array is between 1 and m. And after applying the mentioned algorithm to array, the search cost should be equal to k. Return the number of ways to build array under the conditions. As the answer may grow large, we can compute it modulo 10 to the 9 plus 7. So honestly, this problem is a lot. There's a lot to kind of like go over, but once you figure out what to do, it's actually not super hard. But let's kind of look at these solutions and try to get some intuition. So here we have our first problem. So n equals 2 means the array has to be length 2. M equals 3, which means the elements have to be between 1 and 3. And k equals 1, meaning the search cost has to be 1. So for the search cost to be 1, it essentially means that the first number we encounter has to be the greatest number. Because if we have something like this, then the search cost would be 2, right? Because the numbers are stuff at -1, so we'd get this, which would be the biggest number, which would give a search cost of 1, and then here would be a search cost of 2. So essentially, search cost is just showing, like, where does the biggest number have to be. And so in this example, the biggest number has to be the first number, and you can have numbers equal to it. So if the biggest number is like 1, you can have 1 after it, or you can have numbers that are smaller after it. So if the biggest number is 3, you can have like 3, 1, 3, 2, 3, 3, totally fine, right? You only increment the search cost when you find a new biggest number. So these are all of the outputs. Now let's look at the next one. So n equals 5, which means the array has to be length 5. M equals 2, which means we have to have numbers 1 through 2, and k equals 3. So for k equals 3, that means we have to find like 3 biggest numbers. So essentially we need to find like one biggest number, and then a bigger number, and then a bigger number. But because m is 2, the numbers can only be 1 and 2. So we can only get 2 biggest numbers. So basically, I guess you can check for this if you want to, like, preemptively, to make this a little bit faster. If k is greater than m, then you don't have a solution. So you can just return. Because k equals 3 means we have to find 3 numbers, and m is 2, so we only have 2. Okay. So now let's actually look at the last example. So n equals 9, m equals 1, k equals 1. So what does this mean again? So n equals 9 means we have 9 numbers. M equals 1 means they all have to be 1. And k equals 1 means search cost has to be 1. So essentially, if every number has to be 1, this is fine, because this is going to be the first biggest number we find, and everything else will be the same. So the search cost for this array will be 1. And notice these constraints are relatively small, so we can have a solution that's pretty inefficient. And that's what we're actually going to do. We're going to code up something reasonable that will pass, and then I'll just kind of talk about what optimizations you want to make if you want to code that up. But I'm not going to code up like the super most optimized thing, because I think that's just going to take like an extreme amount of time, and I just want to make something reasonable that you can come up with, and then I'll kind of explain a little bit how you could optimize if you want to. Yeah. So we're actually going to code this up. Notice we don't actually need to return the array, so it's going to be kind of nice. So we just need to figure out the combinations we need. And so because we can use like a lot of these states, we're actually going to code this up using DP, right? And we're going to try to figure out, like, it's kind of tricky to figure out the states for DP, but we're going to try to figure out, like, what are the minimum states for DP. Okay, so let's start off with like what we need for DP, right? So for DP, we need first thing states, which is like usually the tricky part of a hard problem, right? Try to figure out states that will actually, represent everything and still not be too many. So we need states, we need base case, and recursive case. So what do we really need to know for the states here, right? So we kind of want to know, so we're just going to calculate how many arrays we need, but we're not actually going to like store these arrays. We're just going to calculate, right? So for the states, what do we want to have? Well, we probably want to have some kind of like an index of where in the array we are in, right? And then it's pretty easy to add up possibilities. We can either multiply possibilities or add them or something. So we need to figure out, the first thing is, yeah, like where, when we're building these arrays, like what element are we actually on, right? And then what other things do we need? So we probably need to know what's the biggest number we've used so far. And is that enough, right? If we have an index and the biggest number used so far, so the biggest number used so far will tell us like how many, like if we want to use something bigger, what if that increments the search cost. So we are going to need to know that. But is that it? Like, is that going to represent everything? Well, we also need to know, like, what is the search cost so far? And the reason is that you need to know that instead of just the index and the biggest number used so far is, let's say m is 100, k is 100, or I guess 50 or something, right? And n is 50. So the biggest number used so far in the index don't tell you everything alone, because let's say we have something like this. So let's say we have 1, 6. The biggest number used so far would be 6, but we can also have like a bunch of other conditions, right? We can have like 1, 2, 6, 1, 2, 3, 6, and so on, right? And so 1, 2, 3, 6 and stuff, and 1, 2, 6, like those are fine. All we need to know is the biggest number used so far, but we also need to know like how many more how many search costs have we actually done. So like in 1, 2, 3, 6, our search cost is 4, where in 1, 6, our search cost is 2. And you can even have arrays of the same length, right? So you can have 1, 2. So just knowing the length isn't enough, because you can literally just have like 1, 1, 1, 6, where the search cost here is 2 and the search cost here is 4, because we need to figure out like how much search cost do we still need, right? So these are the states we need. We need the index, the biggest number used so far, and the search cost so far. And that's going to kind of tell us everything we need to know. Okay. So for the base case, there are actually a lot that I came up with. Maybe some are redundant, but I tried to come up with like a lot of cases that you can just early terminate, right? And so this is not going to be like the most efficient algorithm. There are definitely optimizations, but at least I made some optimizations for early termination, so it's not that bad. Okay. So obviously one base case is like if we have I numbers, right? Like if the index we are on equals n. So if index equals n, right, we fill out their whole array. What do we want to return? Well, we want to return, is our search cost equal to k? So that's what we're going to return. We're going to return search cost equals k, right? Because if it's less than k, then that's not a valid state, right? And if it's like greater than k, it's not a valid state. We need our search cost to be exactly k, right? That's one of our conditions. Like if we scroll back up here, we need the search cost to be equal to k once we fill that out. So that's one. Now let's look for some early terminations. So what are some early terminations we can have? Well, if our search cost is greater than k, like if our search cost used is greater than k, then obviously this is no good. So we just want to return 0 for this one. So for all these, we're going to return 0. And let's think of some other ones. So the other condition is, what if k minus our current search cost is actually greater than m minus our biggest number? So like, let's say k here is 100 and search cost is, let's say we've used 1 so far, and our biggest number so far is like 2, but then m is only like 10. Well, if we need our search cost to be 100 and we only have m equals 10, we can only have 8 more numbers here. So we're never going to this is never going to work, right? So we can kind of like use this equation to figure out like, can we even have enough numbers here? Like even if we increment even if you keep incrementing by 1, right? We just have like 1, 2, 3, 4, and so on up to m. Can we even do that enough to equal k? And if m is way too small and k is too big, then that means this is going to fail. So if this is false, we can also return, or if this is true, we can also return 0 because we just can't have a solution. And there's one more that I thought of, and let me know, maybe some of these are redundant. These are just the ones that I thought of. So the last one I thought of is k minus search cost so far is actually greater than n minus I, meaning like, so we have some cost so far, right? And then we have some spaces left in our array. So let's say k, once again, is like 50, our search cost is 1, and our array is only length 10. Well, we need search cost to be 50, but our array is just too small, right? So if the array is too small, even if we increment by 1 every time, same kind of thing. If our array is too small or our m is too small, we're never going to be able to get that search cost. So all these can just be early terminations. So these 3 conditions are going to be early terminations, and we can just return 0 for all of them. There might be more, and some of these might be redundant. I haven't done like an insane amount of tests because there are a lot of variables here, so it's not super easy. But essentially, these are the ones that I thought of for early termination. So for all of these, we can just return 0, and then here, we're going to return 1 if our search cost is k. Okay, what about a recursive case? So what values can we try, right? Like, let's say this is possible. What values can we try? Well, we can actually try any value we want. So essentially, what we need to do is we can try any value, like we can try to put in any value we want. So we need to loop from 1 to m because these can all be valid, possibly. And then what are going to be like our DP updates? So our DP is going to be index plus 1, right? We're going to like go to the next index. And then we need to have this biggest number used so far. So the biggest number used so far is just going to be a max of the biggest number used so far. Biggest number used so far. And this like loop number. So we'll call that like whatever, cur or something, right? So it's going to be the max of the biggest number used so far and cur. And similarly, the cost will be the old cost, or it will be cost plus 1 if the current number we're using is going to be greater than the biggest number used so far, right? So let's say our array is like 1.6, and we add a 7, then our cost will go up, and if we add anything 6 or less, it will stay the same, right? So cost will either be cost or cost plus 1, depending on if we add a bigger number or not. And that's essentially it. And then, so if you think about it, anytime we add a new number at some index, we're just going to add that number. Let's say we add 2, and then we're going to add the number of states to build the rest of the array. So we're just going to like add all of these up. We're going to try to put in every single number and add up all of these for the array. And that's pretty much it. And yeah, like I said, we can definitely have anything because there's like a lot of things that are valid, right? So if we have 1.6, you can definitely make these smaller and then bigger, right? So you can even put in like a 1. You can make this anything you want as long as, like I said, these conditions are fine. And then you can have like a 7 later and so on. So like it doesn't really matter what you have. You should be able to put in 1 through at least there are going to be states where you are going to be able to put in 1 through n. Like let's say our length of our array is like 50, m is 50, and k is like I don't know 10 or something. Right? There's going to be like a lot of possibilities for this to work. And so in this case, for this third number, this can be literally anything as long as it's, you do need k to be 10. So I think it needs to be like anything below something in the 40s, right? Because you still need, you do need 10 increases and we only have 2 here. So it's going to be like 42 or 43 or something, but literally anything from 1 to 43 would work. And if k was something even smaller, like let's say k is only like 3, then like this could literally be any number. And so that's what we're going to kind of do. We're going to try every number, and then we're just going to have a bunch of early terminations when something doesn't go right. And so this is going to be kind of how you do this. And then as far as the optimizations you can make, I'll just talk about it briefly. Since we are doing DP of index plus 1, if you actually code this bottom up, because you're only doing index plus 1, you can have like a space optimized bottom up because like you are only going... Whenever you do memoization or bottom up and you are only looking at like the next element across, you can just like space optimize it and only store the next element across instead of the entire index. So that is like, or that's like one of them. There's like a bunch, but yeah, that is like a general trend. Is think about when you recurse, like how far down you're recursing, and if you're only recursing one or two elements, instead of storing an entire array, you can just store that element and then just go backwards. But let's actually code up this memoization, and we'll go over the code and stuff and complexity. So we're going to have a visited array, and we are going to have a mod because this number can get really big. So we're going to mod 10 to the 9 plus 7, store that as a constant variable. Then we're going to have our DP. So def DP. We have an index, our biggest value seen so far, and our current cost. And then we're going to have the base case of if I equals n. That means we are going to check. These are cost equal k, right? So for cost equals k, we're going to return 1. Otherwise, we're going to return 0. Okay. Now we're going to have all our conditions for early termination. So if cost is greater than k, we can't have it. Or k minus cost is greater than m minus biggest. Can't have that. Or k minus cost. So remember, this is the one that m is too small, and even if we tried to increase, m would be too small. And this is the one that, even if m is big enough, we don't have enough space in the array. So all of these, we can return 0. Now we're going to check, obviously, our cache. So if, and you can actually, I don't know if it's faster, it might be. You can actually use a cache decorator. I haven't really done that a lot, but you can just have like add cache in Python, and then that will handle like your visited and stuff. So if you want to do that, you can do that as well. That's already like implemented in. But I'm just going to use the visited instead. So if I biggest cost visited, return visited I biggest cost. Okay, so we're going to have a result equal to 0, and then we are going to loop. So for value in range, we can have anything from 1 to m. So this is m is exclusive. So we're going to try it. So we're going to say, let's add our old result, right? So we're going to add our old result plus dp of, so res equals our old result plus dp of the next index. And then remember, our biggest is going to be max of biggest and the new value, whatever is bigger. And our cost will be, so cost if value is less than or equal to biggest, else cost plus 1, right? So if the new value is bigger than biggest, then we add 1 to the cost. Okay, and then we are also going to mod it here. So we're going to take this, and we are going to mod it. Yeah, mod. Okay, so we're just going to keep it as small as possible. And then we will store it in the result finally. So visited biggest cost res return, and then we should be able to just return dp of 000 without having to mod it because we are modding here already. So we're storing the values as small as possible. And yeah, and I think that should, oh yeah. So our 0 is because I should start at 0. The biggest value should be, you can make it like -1 because these values are, but 0 would also work because these values are from 1 to m. So anything is bigger than 0 as well. And then our starting cost is 0. So we can try to run that, see if we have any errors. Looks like we don't. But yeah, I think this probably isn't too bad. Like, it's definitely not one of the insane hard problems. And like I said, this is okay, but there are definitely optimizations where there's like a prefix sum version as well. But this is good enough for like a hard problem. We're going to go with it. But yeah, so let's talk about the time and space complexity for this one. And also, I think this is like the most intuitive one to code up as well. So a lot of the like hard problems are like the super optimized stuff is like kind of hard to come up with. So I would just more focus on just trying to actually have a solution that's pretty reasonable, which this one is. So let's think of the time and space and all that stuff. So essentially, what are we doing, right? So we do have all these early breaks, but they won't necessarily happen. So we are looping, right? So usually for DP, you want to think about like what are your states, and then is this constant time or not? So for our states, we are looping for n, and then we're looping m cost, right? So this biggest can be 1 to m, the cost can be 1 to k, and then the I can be 1 to n. So n times m times k. Now this is constant, this is constant, this is constant, but here we have a for loop that we are looping from 1 to m. So we are taking all of this and we're multiplying by m again. So this is m squared. So it's going to be n times m squared. So instead of cost, this can be k, right? Because cost can't be bigger than k. If it's bigger than k, we'll just return straight away. So we're not like continuing there. So it's going to be n times m squared times k for the time. And the space, we can just think about like our cache and what's the farthest we can recurse. So obviously the farthest we can recurse is only n, so that's not a concern, right? Like for every, we're going to be recursing n levels deep for every new index. So that's nothing compared to the cache size. So our cache size is n times m times k, right? Because I can go 1 to n, biggest can go 1 to m, and then cost can go 1 to k. And like I said, you can optimize the space to instead of using this dp I plus 1, you can do n in place. If you did bottom up, you can actually optimize the space to be, I think it's like m times k. And so that's totally doable. And then there is another solution with like prefix sums that's hard to come up with. Maybe I'll do a video on that, but I think this one's like the more obvious one. And for a reasonably tough hard problem, I think this one's like clear to understand, clear to get to. So I kind of like those kind of solutions more. Yeah, so that's going to be it for this problem, actually. And if you liked it, please like the video and subscribe to the channel. And I will see you in the next one. Thanks for watching.